Okay, welcome back, everybody. So, at the end of the last lecture, we were discussing the Fourier series. So, we had the Fourier sine series, Fourier cosine series, and the full Fourier series. So, here, just to remind you, here's the full Fourier series for a function. For the full Fourier series, we were considering a function defined on some symmetric interval minus L to L. The full Fourier series is then defined by this, where these coefficients could be computed by these formula. So this full Fourier series contains in it like the Fourier cosine series and the sine series, where the coefficients are slightly different here, right? The integral was for the sine and cosine series were from 0 to L, and this is like 2 over L instead. But apart from that, hold on, my cats are fighting. Let me separate them. Apart from that, there's uh, there's the one of the main differences was that for the full Fourier series we were given function defined on minus L to L. For the Fourier sine and cosine series we were given function defined from 0 to L. Right, that was the window we were investigating for our functions in those cases. So anyway, to see, last time I told you that basically what we want to do now is to see what this thing actually does, to kind of give us an idea that this or give us some hope that this project is going to work out okay. So we actually need to see what these things do, because I'm claiming that this given phi is actually equal to this sequence, or sorry, is equal to this series here, and of course that means that there's some notion of convergence going on in the background, right? So I'm making a statement that this series or its sequence of partial sums converges, say, pointwise to phi of x, right? So there's a lot of convergence statements. We're going to mostly gloss over those. I will go through them and state them, but we're not going to spend any time proving those things. You're just going to have to trust me that everything works out great. And so, what's kind of like a good way of seeing how this works? So let's focus on some examples, right? So let's let's do some examples. So example 1, let's have a look at the function that is identically 1 on the interval that's like 0 to L. Okay. Okay. All right. Well, let's recall our Fourier sine series definition. All right. So the Fourier sine series definition was that this phi, could be written as this sum of these b sub n's times sine of n pi x over L, where the b sub n's were computed via this formula, right? So let's find the Fourier sine series, cosine series, and then the full Fourier series for this thing. So what is the Fourier sine series here? And of course, when we ask the question, find the Fourier sine series, really you could say, oh, well, there it is, right? It's this thing. That's not what we mean by finding it, right? So the sine n pi x over L, we know that that shows up. When we say find the Fourier sine series, really it means computing these coefficients. Okay, so computing these coefficients is finding the Fourier sine series for this function. So we want to compute this coefficient. So how are these coefficients written? This is b sub n is 2 over L times the integral from 0 to L of 1 times sine of m pi x over L dx. What is this? If I just directly integrate this thing, this is 2 over, I have an n pi L here, so this is 2 over n pi times the L cancels here with this L, and so this is 2 over n pi times 1 minus 1 to the n, right? So when n is even, this is going to be 1, so it's going to be 1 minus 1, it's going to be 0. When n is odd, this is going to be 1 minus 1, so it's going to be 2 times 2 over n pi, so it's going to be 4 over n pi. And so I get coefficients 4 over n pi if n is odd, and 0 if n is even. And so my Fourier sine series is, if I write this out, this is sum from n equals 1 to infinity of b sub n sine of n pi x over L, but we've just found that these b sub n's are 4 over n pi if n is odd and 0 if n is even, so all of the even terms are 0 in this sum, and so this is really an odd sum. So it's a sum over odd terms, and when it's odd, each of these coefficients is 4 over n pi, so the 4 over pi can be factored out. So 4 over pi can be factored out. And let's change indices just to make this easier. And this is a sum from, so all of the odd terms show up. So let's let m start at 0 and go to infinity. And so 1 over n, let's write n as an odd number. So that's 2m plus 1. So this is 1 over 2m plus 1. That's the odd terms for 1 over n. Times sine of 2m plus 1 times pi x over L. Okay. And so this, of course, is obtained just by reindexing because only the odd terms are going to show up here. So this is me reindexing and saying let n be 2m plus 1. And if you don't believe that this is going to get everything, you can just write out a few terms, right? The same thing that always applies for series here is kind of the thing you do, which is if you're confused about what a series looks like, write out a few terms and you can convince yourself. So when m is 0, you get the 1 n equals 1 term. When m is 1, you get the n equals 3 term. Yeah, this is going to give me all the odd stuff, right? I'm not too confused here. Okay. So this is what I get for the Fourier sine series. So it is this thing. Okay. Really, of course, this is just my way of, this is just the way of writing it out. Once I know the coefficients, then I understand what this thing is going to look like. Okay. Well, what about the Fourier sine series for the same function? So, or sorry, Fourier cosine series for the same function. So what should the Fourier cosine series look like? Well, again, the function in question is, we're doing this for just the identical function 1 on 0 to L, right? And so what about writing out the Fourier cosine series? This would be me writing out 1/2 a naught plus the sum from n equals 1 to infinity of a sub n cosine of n pi x over L. So I want to compute those coefficients here. Well, when I compute the coefficients here, so this is, a sub n is 2 over L times the integral from 0 to L of 1 times cosine of n pi x over L dx. What do I get here? Well, when you integrate a cosine, of course, you're going to get a sine. You're going to get a sine of quantity that is evaluated at 0 and L, right? And sine of 0 is 0. And at L, it's going to be sine of n pi. So that's also going to be 0, right? So actually, this equals 0 for all n. Is this true for all n? Why did I write not equal 0? This is equal to 0 if n is not 0, right? So there is exactly one 0 here that this works for. So, there is exactly one value of n for which this is not 0. So a naught is 2 over L times the integral from 0 to L of 1 times cosine of 0 pi x over L is also 1 dx. And so this is 2L times L. So this is 2. So a naught is 2. A sub n is 0 if n is not 0. And so the Fourier cosine series here is just 1/2 times 2, right, plus a bunch of zeros, right, forever, if you like. Okay, of course, there's infinitely many terms here, whatever. These are all zeros. So this is just 1. So the Fourier cosine series is actually trivial for this function in a sense. Right? So Fourier cosine function, or Fourier cosine series is actually trivial for this phi. But why? Right? Note that phi, which is 1, is exactly the same as cosine of 0 pi x over L, right? These things are the same. Right? They're exactly the same. So what's the deal there? Right? The deal is that this cosine series, right, lines up with our original function, because our original function is actually just one of the cosine n pi x's, right? It's just one of these values. So of course, the only non-zero coefficient there is going to be the one that picks out that value, right? So this is actually, here's a related question. And you can probably answer this really quickly. What is the Fourier cosine series of phi of x is cosine of, say, 4 pi x over L on 0 to L? Right. Of course, you could do this with the Fourier sine series, having your starting function being some sine here, right? So the idea here is, yeah, the Fourier cosine series is trivial in the sense that I can easily write it down. It's actually just a single term here, because the function you started with was exactly one of these things, right? Of course, I could make this question a little bit more complicated. I could write this as a sum of finitely many of these cosine n pi x over L terms and ask the same question, and you can figure out what the Fourier cosine series would be in that case. Okay. All right. So, what is it that has happened here, right? Well, maybe if we look at the full Fourier series for the same function, the question maybe is a little clearer. What about the full Fourier series? So, what about the full Fourier series of the same function, v of x is identically 1, on minus L to L? Okay. So, what is the what am I going to get here, right? Note, v of x in this case is even on minus 1 or minus L to L, right? It's even on this interval. So, the full Fourier series, let's remind ourselves, what does the full Fourier series look like? Here's what it looks like, right? So the full Fourier series in this way looks like what? Well, what's going to happen here is, well, this should work out in such a way that, again, because the full Fourier series contains, say, this coefficient, this a0 coefficient corresponds to this cosine of 0 pi x over L term, which is exactly the function phi in this case. So what we're going to do is actually recover just this same trivial series that we did before, right? We're just going to recover the same trivial series. So we just recover the trivial. I want to say trivial in the sense, a lot of times when you say trivial, you mean identically 0. It's not that it's trivial in the sense that it has finitely many terms and actually just has one term. Right, so we recover this trivial Fourier cosine series. Right, which is just a0 is 1 and a sub n and b sub n are all 0 for all n not equal to 0. Okay. Now, let's look at plots of these things. So let's look at plots with, we'll pick L equal to 2 here, for each of the Fourier sine, cosine, and full Fourier series. But then when we write out the Fourier sine series and we're talking about plots, really how we want to do this is to plot a bunch of partial sums of this thing, right? So let's look at this, right? if we choose L equals 2, whatever. I'm just going to write it like this anyway. For the cosine series, all right, this would be 1/2 A naught plus sum from n equals 1 to big N of A sub n cosine n pi x over L. And for the full Fourier series, same deal. We're just doing partial sums here. All right, so let's do this. For this example, let's do n equals 2, 5, 10, and 50 to see what it is that's going on here. Okay, and we're doing this on the interval, so these would be on interval 0 to 2, and the full Fourier series would be on the interval -2 to 2. So let's draw, so first of all, let's draw our function phi. So here's 0, we'll say here's 2. Right, and so our function, if this is 1, here is our function phi on 0 to 2. Right, and I'm going to add in dotted lines for the rest of the function. Okay, but this is the piece that we're looking at here. Okay. Now we're going to be plotting these corresponding partial sums here and looking at kind of what they look like. So let me bring up a picture of plots here. So this is for the Fourier sine series. All right. So why are we not doing the Fourier cosine and full Fourier series? Because for this example, those things are trivial. So the Fourier sine series was the only one that wasn't trivial for this example. And notice what's happening, right? So pay attention to this picture, right? We're interested in 0 to 2 here, right? This is where our phi lives, 0 to 2. But of course, what you notice is that this sine series, because the only argument, right, where x shows up here is right here in a sine. You know that sine's defined everywhere. So this Fourier sine series is going to be defined on the whole real line, right? So even if our initial function was defined, say, from 0 to 2, this Fourier sine series is going to be defined everywhere. So then what is the meaning of this? Well, let's look at this picture. So plotting these partial sums, for the n equals 2 case, it looks like this. Okay, so you see this is not that close to our constant function 1 on this interval, 0 to 2. At n equals 5, you see between 0 and 2, it's getting close to being just 1 here, right? It's got a little bit of oscillations here at 1. At n equals 10, it's getting much closer, right? And at n equals 50, so 50 terms in my sum here, this is definitely getting really, really close to phi of x equals 1 on 0 to 2. Now, what is it doing off that interval? Right? So what's it doing off the interval 0 to 2? Well, like what is this thing that I've drawn in here? It's 1 here, but it's like -1 from -2 to 0. And then it goes back to, it's 1 here, and then it would be -1 over here. Here it's -1, it'd be like 1 here. What is it that's going on here? What is this Fourier sine series doing to phi? It's taking my function, right, phi of x, which is just identically 1, right? I've drawn in the dotted line how that is. And it's like doing its odd extension from -2 to 0. So my phi is defined from 0 to 2. It's doing the odd extension between -2 and 0. And then it repeats it. So it's doing like an odd extension, and then it makes it periodic. All right. So it seems like the Fourier sine series takes phi on 0 to L, does its odd extension on minus L to 0, and then repeats after period. Let's look at our picture. So what's the period here? So I go from here it's minus 1, here it's plus 1. Now I'm back to minus 1 again. So this is at minus 2, this is at 2. So period 4, or 2L. All right. So after period 4, which in this case was 2L, right? 2L was 4 here. So it does odd extension from minus 2 to 0, so that from minus 2 to 2, it is this like odd extended phi. But on a larger interval, say minus 4 to 4, it's clear that it's like this odd extension made periodic. Okay, so have a look at those pictures again if you're confused about how this works. Of course, as I mentioned, the cosine and full Fourier series are actually trivial for this particular example. So let's pick another function and see how this works. So let's do example 2 here. What about phi of x is equal to x on 0 to minus 2? Okay. Or more generally, there's nothing special, or why did I write 0 to minus 2 here? Let's do this on 0 to L. And of course, we'll pick L equals 2 in our specific plots, but there's no reason why we have to do that. This just gives us something to work with here in these pictures. So now let's see how this works. So let's look at the Fourier sine series. Well, the Fourier sine series now is its coefficients, right, are going to be 2 over L times the integral from 0 to L of x sine n pi x over L dx, which just by direct integration, right? Remember how you might integrate this thing. Right, so this is going to be 2 times minus 1 to the n plus 1 over n pi. Okay. So the Fourier sine series is going to be sum from equals 1 to infinity of b sub n sine of n pi x over L. This is going to be rewritten here as 2 L over pi times the sum from 1 to infinity of minus 1 to the n plus 1 over n sine of n pi x over L. Right, so there it is. What about the Fourier cosine series? Now you might say, well, like what if I wasn't able to find these in a super nice way? Right? What if these integrals were actually harder to compute? Well, then maybe you have to use some other kind of method to do this. Maybe you have to use some certain computational methods to generate these things. Of course, selection bias applies here, right? We're typically going to deal with these coefficients where you can actually do this integration so that you can actually write out some nice closed form, a Fourier sine series. You don't have to write something horrible here because the coefficient integrals are terrible, right? So for us, this is all going to work out reasonably well, right? This is an example of reasonably well here. Those coefficients aren't too complicated. What about the Fourier cosine series? Well, let's compute in the A naught case. A naught is L, right, which you can directly compute. A sub n is 2 over L times the integral from 0 to L of x cosine of n pi x over L dx. Now this is no longer 0 for all of these n, right? In fact, it's only 0 for half of them. So this is minus 4L over n squared pi squared if n is odd, and 0 if n is even. Again, we can just do this with direct computation. So we can just directly integrate that thing, and this is what we get. And so the Fourier cosine series, right, 1/2 A naught plus the sum from 1 to infinity of A sub n cosine of n pi x over L. What is this? This is L over 2 minus, since this is negative in every single one of these things, this is minus the sum from, we can re-index this to sum over the odd integers, so this is m equals 0 to infinity here of 4L over 2m plus 1 squared pi squared cosine of 2m plus 1 pi x over L. Right, so there it is. There's my Fourier cosine series. Okay. Now, what about the full Fourier series? So what about the full Fourier series for v of x equals x? Why did I write identically equals here? V of x equals x on, we'll say minus L to L. Well, there's two ways you can do this. You can compute this directly from the definition of these things, and you'll get your answer. And if you do that, you will notice, okay, so if you directly compute via the definition, you will notice that the full Fourier series of phi of x equals x is identical to its Fourier sine series. Maybe put an exclamation mark on that. Why would this be the case? And why? Now, why would this be the case? As we'll see, because phi is odd. Ah. Hmm. Hmm. Well, this meshes with our previous example, right, where the phi in question was just a constant function, which was even, right? And we saw that its full Fourier series and its Fourier cosine series agreed. They were the same, right? They were both this trivial series that had a single non-zero term in it, right? So because the phi was even, its full Fourier series and its Fourier cosine series were exactly the same. Or maybe you just viewed them as incidentally being the same, but that turns out to be the reason why they're the same. Similarly here, the reason why the full Fourier series for phi of x equals x is the same as its Fourier Fourier sine series is because phi is odd. Okay. So this is now you might say, wait, its Fourier sine series is defined for a function on 0 to L. Full Fourier series is defined for a function on minus L to L. Yeah, but both the full Fourier series and the Fourier sine series are both defined on all of R, right? So we'll be kind of stressing these things over and over again. Okay. So this is identical to its Fourier sine series, even if we had given phi of x only on 0 to L, right? On 0 to L. Right, but both of these things would be the same. Okay. Let's plot some terms. So let's plot some partial sums. We'll say n equals 2, 5, and 10 should be enough to see what's going on. Okay. So let's see how this goes. So what you're seeing in the top row is a partial sum of the first 2, first 5, and first 10 terms, respectively, right? And these are in the Fourier sine series. So this is for phi of x equals x. Notice what's happening here, right? So again, our phi of x, maybe I should stress this. Let's go back here. So we are talking about phi of x on, we'll say 0 to L, and we'll take L to be 2, okay, like we did in the previous example. So phi of x, we've said, is x in this example. And so let's say here's 0, here's 2. So there's phi of x. And of course, this continues. Right? We know that. That's what phi of x is off of 0 to 2, but this is the piece we're interested in. So what is it that's going on in these pictures? So let's first draw our attention to just what happens from 0 to 2. So from 0 to 2 here, what happens? So from 0 to 2, I have this thing is trying to be like x, right? Here in the n equals 5 case, it's getting a little closer. In n equals 10, it's getting a lot closer, right? Okay, so on 0 to 2, it definitely looks like there's convergence happening here. What's going on off 0 to 2? Again, it looks like what is happening here is odd extension, right? So the odd extension here has occurred. And so it looks like I have, like, the Fourier sine series has odd extended this piece from 0 to 2 to minus 2 to 0. And then, but it keeps going, right? This is defined for all of R, and so it keeps going. And so how does it keep going? It looks like, okay, it took the initial piece, it did the odd extension from minus 2 to 0, and then these other pieces it tied together by periodically just repeating them, right? So it's like there is this periodic of period what? 4 again, so 2 times L. right? So it's doing odd extension and has period 2L. Okay. What is happening for the Fourier cosine series, however, if we look at this? So again, first draw your attention to 0 to 2. What's going on here? I have convergence here. Nice. Okay. Then what is happening from -2 to 0? Well, let's see here. How's this been extended? This piece from 0 to 2 has been extended from -2 to 0, and then repeated again. Okay. So there's kind of a unifying theme here. What it is that's going on in these cases is you have function defined on your initial interval 0 to L, but all the Fourier series involving this thing, right? So the Fourier series that this thing is supposed to be the limit of, right? These are supposed to be converging to. Uh, those Fourier series are defined on all of R. So what's going on is it does look like, as n increases, there's convergence on the interval in question. But these Fourier series are all defined for all of R, right? And so what they do for all of R is they take this, they extend it, right? They extend it to -L to 0, in this case -2 to 0, and then periodically repeat it, right? So in the sine case, it looked like this is the odd extension, right? In the cosine case, what did this look like? Well, again, right? Here's the picture. Okay. Well, in this case, I should say, right, we saw that the full Fourier series agreed with the Fourier sine series. And so you could have likewise considered that first row of pictures, right? This row of pictures could be thought of as the full Fourier series for phi as well. Let's do one more example, and we're not going to write out the coefficients for it because it would be kind of annoying to write these out. So we're just going to generate plot of this thing. So one more example. What if phi of x is defined to be, we'll say 0 if x is in -2 to 0, okay, and x if x is in 0 to 2. Okay. So here is phi of x defined on -2 to 2. What does its full Fourier series look like? So the function, of course, is easy to draw. If here's -2, here's 2, then this function is 0. And then from here up to 2, it is x, right? So this is what phi of x looks like. So let's look at its Fourier, or its full Fourier series, so that we'll do values n equals 1, 4, 6, 16, and 21. So that's how many terms would show up in the full Fourier series. And so what does this look like? Oh. So you can actually see how this convergence is happening. Now, again, as before, off of this interval minus 2 to 2, the full Fourier series is still defined for x that aren't on that interval. So what is occurring after that is this is made periodic. You can kind of see what's going on the end here and the end here. This piece is copied and tied together, right? So this is made periodic. Let's put all of this into words, all these observations here. Okay, so how do we view the three Fourier series as functions over R? How do we view these Fourier series as functions over R? And the answer is the following. So there's the Fourier sine series. So firstly, so the Fourier sine series for phi of x on 0 to L. How does it behave? Right. While phi of x is defined on 0 to L, Fourier sine series is defined, the Fourier sine series is defined for all x in R. Okay. And since it is comprised solely of odd functions, with period, so they're odd functions that are periodic as well, with period 2L, the Fourier sine series is an odd function that is periodic with period 2L. Now, how was this obtained? Right? How this was obtained is you took phi, and it doesn't matter what phi is, whatever phi was, phi is defined on 0 to L. On minus L to 0, you took the odd extension of phi, and then you just like kind of copy pasted that piece together, tying them together in some way that's is a very, very loose way of saying how this works, right? So everything was continuous, right? This is definitely continuous, right? But there were these things that looked like jump discontinuities going on. They weren't jump discontinuities, right? The Fourier series adjusted in each case. Let me bring up the picture again. This is kind of a classic example of the sort of thing I'm talking about here. So you notice that it's like what's building up here looks to be like a jump discontinuity. It's not. This is still a function. This is still all continuous. And for any partial sum, this is going to look like this. Right? So it doesn't matter how big n is. N could be 100 million. You're still going to get a continuous nice thing. It's just that this bit connecting them is going to get steeper and steeper and steeper. In the limit, that can go to a jump discontinuity. But for each of these partial sums, it's not going to. It looks like this. Okay. And so that is what it is that's going on here. The copy pasting bit, basically I would take my function phi, odd extend it to minus L to 0, and then copy that odd piece over and over again with period 2L. Okay, that is what's going on here. Similarly, I don't want to rewrite all of this, so Fourier cosine series for phi of x on 0 to L. It's the same sort of thing, but it's comprised of even functions, periodic with period 2L. So it is an even function, periodic with period 2L. And so this thing that it does, let's go back here. What it is that happened is that the Fourier cosine series took this piece from 0 to 2, did its even extension from minus 2 to 0. Right, if you figured that out now. It did its even extension here, and then copied that piece, right, over and over again. Now it turns out that copying that piece worked out fine there because those ends matched up, right? So this is another thing we're going to see going forward. Maybe I'll bring this back for a second. Notice that up here I have what looks like a jump discontinuity building, because the endpoint here and its endpoint when I've done this periodic copying, the left endpoint don't match up, right? They're different, so there's this like jump to reach from here to here. But that didn't happen in this case because when I do this periodic copying, the endpoints at the left and right ends actually match up, right? So they match up, and I didn't have that sort of thing happen. Okay. So the Fourier sine series is odd and periodic. The Fourier cosine series is even and periodic. And the full Fourier series for phi of x on minus L to L, it's neither even nor odd necessarily, but what we can say is that it is periodic with period 2L. Okay. It might be even or odd, as we saw in 2 of the 3 examples we did. The full Fourier series actually agreed with either the Fourier cosine or Fourier sine series, and so in that case it was even or odd, right? But it need not be, right? It need not be. Whereas Fourier sine series is always odd, Fourier cosine series is always even. Okay. Now, we are not going to prove convergence. You're just going to have to trust me that for reasonable functions phi, the Fourier series converges pointwise to phi on the interval in question, right? So for now, assume that for phi reasonable, okay, the 3 Fourier series in question for phi converge pointwise to phi on the sampled interval. So this is either 0 to L or minus L to L, right? So this is okay. Now, I mentioned at the very beginning, what about at the endpoints in question? So it turns out that the values of phi at the endpoints doesn't matter. This is very convenient. This is very nice. But why would this be the case? Well, remember that all of those coefficients, right, all those Fourier coefficients involved in defining these Fourier series for phi involve integrals, right, over the interval in question. And because they involve integrals, right, um, it is reasonable to think that, oh, well, like the actual value of phi at the endpoints in question doesn't really matter that much, right? So we're integrating over the intervals, so the actual individual values at those endpoints is not super super important here, right? I don't need to necessarily know the values of the integrand at those endpoints, right? Now, you know, these boundary values can factor in other ways, but it actually didn't matter, right? We had this, you know, let's just go back to our nice example here. We had this picture where what phi did at the ends didn't really matter because what's going on is there's this jump discontinuity developing in the Fourier series, but the Fourier series had a way of, you know, like what's going on here does depend on the values of phi in some way, but whatever's happening, it doesn't matter because this Fourier series is it's going to smooth it out for in the partial sums. There may be discontinuities in the limits, as we'll see, but it doesn't matter. These things still have the properties that we want. Okay, and so that's another way of thinking about why the values of phi itself don't actually matter at the endpoints. Okay. So in order to talk about this this convergence of these things, we should mention what it means for a function to be piecewise continuous. So first, let us define piecewise continuity. Of a function. So you may intuitively have already heard this defined as, oh, it's a function defined on some interval where there's finitely many pieces or finitely many values, right, at which it's not continuous. But let's write out specifically what we mean and what we assume happens at those values. So these definitions and these statements that I want to make are fairly long-winded because they kind of have to be. So in order to not spend my time just copying a novel of definitions here, I'm going to put this on screen and read over it really quickly. So here we go. So here's our definition of a piecewise continuous function. So a function phi on an interval a to b is piecewise continuous if the following hold true. 1, it's continuous at all points in ab except if perhaps a finite number of points. 2, at a discontinuity point x, it has a jump discontinuity, right? Meaning that the limits from the left and right, phi of x plus and x minus, where those are the limits that you think they would be, right? The limits coming from the right and coming from the left. Those both exist and are finite. So the types of continuities, let me stop here for a second, or the types of discontinuities that can exist for piecewise continuous. Here's an example of something that is not piecewise continuous on, say, 0 to 5. Something that does this. right? That's no good. Even though it's continuous everywhere here except say at even a single point, right? Something like that is not good. If you want to deal with something like this, there's other things we could talk about, but for us, when we say piecewise continuous, is not what's included here. So what's included, of course, is something like this. So we'll say here's -4 and here's 5. So something like this. Right? That's fine. Okay. So this sort of thing is piecewise continuous. So this piece is continuous, this piece is continuous, this piece is continuous. There's only 3 total pieces, right? There's only 2 discontinuity points. Okay, so let's go back to this. Okay. And the limits at the endpoints exist and are finite. So phi of a plus, that is the limit approaching the left endpoint from the right, and phi of b minus, which is the limit of phi approaching the endpoint from the left, both of those exist and are finite, so it's not allowed to go off to plus minus infinity at the ends. Okay, so that's the other thing. So this sort of behavior is not allowed at the ends either, right? So we can't have something like this happening at one of the ends. Okay. All right. Okay, so that is what we mean here. Let me give one more. This is the full text box for it. Okay. A function defined on all of R is piecewise continuous if it is continuous except possibly at a sequence of values wherein it has a jump discontinuity. Moreover, the distance between any of these discontinuities is bounded below by some positive number. Okay, that's a quick way of thinking about it in words. Now, why is this important? Well, if we are going to do this pasting, right? I mean, and of course we are not doing anything here, right? The Fourier series is taking care of all of this for us. But if we're going to have some thing that's doing the thing that's being suggested here by these pictures, then us saying, oh yeah, it just takes this, it extends it in this way, and it's fine, and I can do that, and then it periodically pastes them together. So it's like I do like an even or odd extension, and then I do a periodic extension, right, which we haven't really done before by this copying and pasting operation. Well, those types of things are only going to have a hope of being well defined if your phi is something like in this definition we've given, this piecewise continuous object. And so, given a continuous function, given a continuous phi on AB such that this limit phi of A plus, so that's its limit from the right, and phi of B minus is the limit of its value at the right endpoint from the left, right? Both exist. So given a continuous phi such that these things both exist and are equal, we can define, we may define phi of A and phi of B. There's like a string here, so phi of A can be defined to be phi of A plus, and phi of B can be defined to be phi of B minus, but both of these things are equal, and so all of these are equal, right? So then we can extend phi to all of r by periodicity to construct a continuous function on R which is periodic with period b minus a. So to construct a continuous function on R that is periodic with period, the length of that interval. So, i.e., for x in, say, b to b plus b minus a, right, then the next window to the right, we just repeat the function. We repeat phi as on the interval a to b. This new interval has the same length as this interval, so we can do this in a nice way, right? And at all joining points, we define the extension. So we define the extension to be phi of a, which is equal to phi of b. This is called the periodic extension of phi. This is called the periodic extension of phi to all of R. This is one of those things where it is easier to kind of intuitively describe this without using precise language than it is to actually write out what you mean. So if writing it out in this way is slightly confusing, the easiest thing I would say is to, as I said, just think about this kind of more loosely or informally. How I'm taking this function and I'm like copy pasting it, right, a bunch. And of course, I'm joining up the ends if I can. I can't always do that, of course. Sometimes we have discontinuity, right? If we have discontinuity, then what we can do is at the joining points, we could just pick one of the ends, right? If we have some discontinuity, we could pick one of the ends as my defined value. But we could also pick like the average of the values if you wanted to, right? So since both these limits exist and are finite, you could take the average of the two, and that would work just fine. And so let's actually see how this works, or now let's see what to do in the event that I have some finite number of discontinuities. So what do we do if phi has finitely many jump discontinuities? Right, so phi of a plus is not equal to phi of b minus. What do you do? Well, we can still do the exact same, but at the joining points, we have to make a choice. Now, we could pick, as I said, we could say always pick the left-handed value, right? We could always pick its value at the left end as being the value there. We could always pick the value at the right, right? We could always pick their average, right? We could do all of those things regardless of what we do in that way. Assume that we've done that. The resulting extension to R is periodic and piecewise continuous. So the only difference here is that the resulting extension is also piecewise continuous instead of continuous, whereas here in this one, this was continuous. So this periodic extension was continuous on all of R because it didn't have those jump discontinuities, right? But we began with a phi that was continuous. So then its periodic extension can also be made such a way that it's continuous. We begin with a phi that is piecewise continuous. Well, then the resulting periodic extension can also be piecewise continuous. That's fine. Okay. Now, so finally, we can precisely state what each of these things are. So finally, we can make precise these previous notions, I'll say, about what exactly the Fourier series do. Okay. So, again, this is a pretty long-winded set of statements here, so I think it's best if we go over these together with the convergence results. Again, I'm not going to prove the convergence, but here they are. Okay, so under certain smoothness assumptions on phi, the following convergence results hold true. So first, for any fixed x inside the sampled interval at which phi is continuous, each of the Fourier series converges to phi of x. This is pointwise convergence. The Fourier sine series for phi of x on 0 to L is defined for all x in R and converges to the odd periodic extension of phi. This extension is obtained by considering the odd reflection on minus L to 0, extending the resulting function by periodicity, period 2L, to all of R. The value of the series at integer multiples of L will depend on the properties of phi defined on 0 to L. So again, if phi was continuous, like whether phi is continuous, piecewise continuous, is going to affect whether the extension is. Maybe some discontinuities build up, even if phi is continuous. Maybe some discontinuities build up here. So in the previous examples, we saw this discontinuity building up. So the thing is that how this behaves on those, we'll see. So we'll see an easy example of this previously. I'll go back to that picture and then I'll draw another picture, or I'll show another picture here in a second. Next, the Fourier cosine series for phi of x on 0L is defined for all x in R and converges to the even periodic extension of phi. This extension is obtained by considering the even reflection on minus L to 0 and extending the resulting function by periodicity, period 2L, to all of R. The value of the series at integer multiples of L will depend on the properties of phi defined on 0 to L. Okay. The full Fourier series on minus L to L is defined for all of R and converges to the periodic extension of phi. The values of the series at those problem points, right, will depend on the properties of the original phi defined on minus L to L. At any point where the odd even periodic extension has a jump discontinuity, the Fourier series will converge to the average of the limit of phi from the right and left. Such jump discontinuities can occur at either of the following: points inside the sampled interval and their odd even periodic extensions where the function phi has a jump discontinuity, that's one. Endpoints of the sample interval. So, even if phi began as being a continuous function, these for the Fourier sine series, Fourier cosine series, these things could have jump discontinuities in them, in the limit. Okay? And so let's see a previous example of that, right? I'm going to leave it blurred out for a second because I'm coming back. So here, this was exactly what we had in this case. Remember what the function was that we were doing. So phi of x is x. That's continuous everywhere. What happens here is that for the Fourier sine series, you see that at the endpoints of the intervals, right? So I began with the interval 0 to 2, of course. So at this endpoint 2, I have a jump discontinuity developing in the Fourier sine series, right? So when I do this copying, this extension, there's this jump discontinuity that's going to be introduced in the limit. So notice, as I said before, there's no discontinuity for any n. Pick any n you want to, right? N equals 10 million, 10 billion, whatever. Okay, that partial sum is still going to be defined on all of R, and it's going to be continuous everywhere. You're not going to have those discontinuities. These discontinuities are only going to arise in the limit, okay, which is the Fourier sine series, right? Is the limit of that sequence of partial sums. And so the Fourier sine series is developing a jump discontinuity, even though the function itself was continuous. The Fourier cosine series, however, does not have this jump discontinuity. And this had to do with the fact that the values at these endpoints match up. Right? That's really what it means. Is that when you took x and you did its even reflection on minus 2 to 0, now the endpoints match up. When you took x here and you did its odd reflection, now the endpoints don't match up. Right? They have different values. But here, doing this even reflection, now the endpoints match up, and now we have, in the limit, there would be no jump discontinuity here. Okay. Okay. Let's see another example of this. So what about e to the x? All right. So I'm going to define three functions. So f sub 1 of x is defined to be the sum from n equals 1 to infinity of, we'll say, b sub n sine n pi x. We'll let f sub 2 be the sum from, maybe I should write here, since I want this to exactly match up, we'll write this as a naught over 2 plus the sum from n equals 1 to infinity of a sub n cosine of n pi x. And let f sub 3 be c naught over 2 plus the sum from n equals 1 to infinity of c sub n cosine of n pi x plus d sub n sine of n pi x, where I'm not going to rewrite all of these. I'm just going to show you what I want them to be. So where a sub n is 2 times the integral of 0 to 1 e to the x cosine n pi x. B sub n is 2 times the integral from 0 to 1 e to the x sine of n pi x. C sub n, d sub n are similar. They're just defined on minus 1 to 1 instead. Okay, so question I have then, okay, if I've done this, note. So A sub n, B sub n, C sub n, D sub n are given by those formulas that I mentioned. So note, obviously these are Fourier sine, cosine, and full series for phi of x equals e to the x on the interval 0 to 1. Okay. So the question is, what do these look like over R? What do these look like over R? So now I'm not plotting I'm not plotting the partial sums. I'm actually plotting the Fourier series here because I want to know what they look like. Okay. So remember, f sub 1 is the sine series, f sub 2 is the cosine series, f sub 3 is the full Fourier series. So let me zoom in here. So the cosine series looks like this. From 0 to 1, of course, this is e to the x, right? So, oh wait, wait a minute, these have been mislabeled here. Okay, so these have been slightly mislabeled. F sub 1 and F sub 2 have been swapped here. So, okay, so we'll have to fix that. So then this is F sub 1, this is F sub 2, this is F sub 3. Okay, these labels are wrong. So this is the sine series. So I have e to the x, so this is e to the x from 0 to 1 here, right? And then an odd extension to minus 1 to 0 has occurred, and then that has been copied. There are jump discontinuities, right? There are jump discontinuities here at the endpoint 0 and at 1. There are jump discontinuities, and those are propagated in the entire series like this. Okay? So this is what the Fourier sine series looks like. The Fourier cosine series took this piece of e to the x from 0 to 1, did its even extension, okay, from minus 1 to 0, and then copied that piece. Okay. And then here, the full Fourier series, remember this is now for e defined on minus 1 to 1. So here's my original piece. And then that has been periodically extended in this way by just copying that piece over and over again. Okay. Notice the main difference here is that to make this sensible, what has happened is at this jump discontinuity, the value is the average of the values at either end. Okay. Similarly, if we go to the jump discontinuities back over here, it's kind of hard to see in this picture. If you go back to the jump discontinuities over here, the value of the Fourier series at each of these jump discontinuities is the average of the values, which in this case turn out to be 0. So here, the average of the values at the discontinuity is 0 because it's the average between these two. Similarly, at this jump discontinuity, the average of the value is also 0. So at each of those jump discontinuities, the Fourier series is 0 here. So this is the Fourier sine series. For the full Fourier series, the values of the jump discontinuities are here. This is like e plus 1 over e over 2. Okay. Okay. All right. So, again, I stress that notice that none of those jump discontinuities actually arose when we were considering the partial sums. These only arose when we passed to the limits, and that's expected. That's how these things should go. Now, the big question that we'll answer tomorrow: what does all of this stuff have to do with solving PDEs? The answer is that these sines and cosines are examples of eigenfunctions and have properties that allow us to say that certain solution spaces to problems we're interested in are filled out by these functions. And this is really the heart of these Fourier series. So these Fourier series are at the heart of this. So there's going to be the second order PDEs that we're talking about, which will involve all of the big three that we've already discussed. Okay. And our idea, or rather, the first thing we're going to do is we're going to notice that there's some tie-in between all of this stuff and linear algebra. There is some analogies that are more than just analogies. It's just a straight carryover from linear algebra. And all of these statements that we were able to make, maybe you didn't see when you took linear algebra, maybe you didn't see how nice those things were in the context of linear algebra, but when you realize, oh, function spaces are examples of infinite dimensional vector spaces, so a lot of these same sorts of things I was saying about vectors, I can say about infinite dimensional vectors or functions. And now these statements are a lot more maybe convincingly powerful. If you weren't convinced that some of these statements about having a basis were powerful in linear algebra, you'll be a lot more convinced that they're powerful when the vectors you're talking about are functions. So then next, brief detour into linear algebra before we finally get to the separation of variables algorithm. And you might say, wait, there's, you've only got 2 weeks left in the course, right? 2 weeks worth of lectures, right? So after today, like 9 more lectures or something. The thing is that once we get to the separation of variables algorithm, from there on, it is just cranking out examples and practicing using this algorithm. So once we get there, basically for the rest of the course, we are just doing examples. So tons and tons of computation. So if you're, a little bit allergic to a lot of the conceptual proof type stuff, then you'll definitely like what's coming with the separation of variables algorithm, because it is pure computation. It is pure grinding computation. And that's kind of the way it is. So anyway, we'll do that tomorrow. So we should be brushing up against, we'll start talking about our separation of variables algorithm tomorrow. So anyway, I will see you then.